Good morning. This is working, right? Good. So this is a bit of review of what we did yesterday. So we started with with the action for a scalar field phi, capital Phi in Minkowski space, something that's familiar to everyone, the simplest thing you can imagine in quantum field theory. Then we promoted this action to curved space, and eta mu nu goes to g mu nu, and derivatives go to covariant derivatives. Covariant derivatives of a scalar is just a normal derivative, but that's a prescription we're familiar with now. So after we promoted it to curved space, we specialized to homogeneous isotropic flat spaces to FLRW. And we ended up with an action that didn't look familiar, so we had to do some transformations to get it to a familiar looking action. In particular, the transformations we did was to define a new scalar field phi, which is the scale factor A times capital Phi, and expressed it in conformal time. And again, a notation alert. A is the scale factor, but eventually we will have ladder operators, which are also denoted by A. And the ladder operators should have an index on them, k, the wave number. When we express the action in FLRW in terms of the new scalar field and conformal time, we get sort of a familiar looking equation of motion for the scalar field, this new scalar field. And we also have a canonical kinetic term in the action. Since we are going to quantize the theory, we have to have a canonical kinetic term. And the equation of motion is phi double prime. Again, prime is the derivative with respect to conformal time, plus grad squared phi plus a squared m effective squared phi is equal to 0. And here, a squared times m effective squared is a squared m squared plus 1/6 1 minus 6c times a squared r. So we also allowed, when we went to curved space, a term in the action, or in the Lagrangian, that was 1/2 c phi squared times the Ricci scalar. That this, in Minkowski space, the Ricci scalar vanishes, of course, so you would not encounter this term in Minkowski space. But in general, we can add it, it's a dimension 4 operator. So from the point of view of effective field theory, there's no reason not to include it, but there's no compelling reason to include it. Furthermore, as people remarked, there should be a renormalization group equation for C. So C need not be a constant, but we're going to assume it's a constant and ignore the running in C. So this in Minkowski space, it would just be this a squared m effective squared term would just be m squared. So effectively, the effective mass of this field is changing as the universe expands. It changes with eta. And this is the crucial piece that leads to particle creation. So a simple way to think about this, not even in quantum field theory, is just thinking about a harmonic oscillator in quantum mechanics. So the expansion of the universe causes an explicit time dependence in the action for spectator fields. So the action will not be Poincare invariant. So the initial state, which we will take a Minkowski early time vacuum, may not evolve to a final state today, which is approximately Minkowski space, but to an excited state populated by particles. And again, you can envision how this happens just by looking at a simple harmonic oscillator. So if you imagine you have some initial state with some potential, and this is just an illustration of what the wave function might be, and it now, if you slowly change the mass, slowly change the spring constant, slowly change omega as a function of time, change it slowly, adiabatically, and we'll have a definition of exactly what we mean by adiabatically, the wave function will slowly respond to the change in the potential, and the ground state wave function would just be different. But now if you non-adiabatically, violently, abruptly change the spring constant, then the wave function will not respond to the change, and the wave function for the new potential will look like it's an excited state rather than the ground state. So we're going to have an expanding universe, and if the universe expands non-adiabatically, then the wave function will change, and you will end up with an excited state. And in quantum field theory, this would be interpreted as a state with particles. So continuing the review, just following our nose in quantum field theory, we're going to write the wave function as a function of conformal time and space in terms of mode functions, do a Fourier expansion, in terms of ladder operators, AK and AK dagger. And the mode functions U of K, we're going to write in terms of the mode function chi k, which is a function of time. We're going to do a Fourier expansion times e to the I k dot x. So we're going to look at different Fourier modes of the field. And the A and A dagger are the ladder operators. And in quantum field theory, the ladder operators obey the commutation relation written there, and other combinations, other commutators of ladder operators vanish. A vanishes, A dagger vanishes, etc. All right, then we saw that the wave equation for chi, so if we put chi in this form into the equation of motion, the wave equation is chi k double prime plus omega squared chi, omega of k squared times chi is equal to 0, and omega of k squared is k squared, that comes from, sorry?
The final gradient should be by equation of motion.
Thank you. Up here? Thank you. So I took a course in electrodynamics from John Wheeler. And he would come in every course, at every class, with a bag of pennies. And every time someone found an error in something that he wrote, he would pay them. It was just a penny, but it was always a matter of pride to be paid by John Wheeler. So I owe you a penny. I guess I could go broke in this series of lectures. All right. So the wave equation is written in this form. And as I mentioned, let's see, here, R can be smaller than 0. The Ricci scalar is negative in de Sitter space, so we expect it can be negative during inflation. So the effective mass squared can be negative. So if we have a harmonic oscillator with an effective mass squared, we expect the mode to increase. It'd be tachyonic in some sense. All right, so in the dispersion relation, the angular frequency squared will play a big role in what we're doing. The latter operators are associated with the mode functions, define a vacuum. And the vacuum is defined to be annihilated by all of the AK. Now, the choice of the mode functions is arbitrary, as long as it obeys the Wronskian condition and things like that. So we can write the solution in terms like we did here, or we could write it in terms of some other mode functions, chi k. So I've defined a mode function chi k in and a mode function chi k out. Associated with those mode functions are ladder operators A in and A out. And we can move back and forth between these in and out mode functions via a Bogoliubov transformation. And chi k and the Bogoliubov transformation is defined in terms of Bogoliubov coefficients alpha of k and beta sub k. And I could have another, I could write chi k out as alpha of k chi k in plus beta of k times chi k star in. And similarly, the latter operator associated with A out, with chi out, can be written in terms of the ladder operators associated with the in state, again in terms of the Bogoliubov coefficients. Now we have a differential equation, a second order wave equation. We want to solve it with certain boundary conditions. And the boundary conditions we're going to take is that as eta goes to minus infinity, that would be the beginning during deep in the inflationary era, that is going to look like Minkowski space. So chi k in is 1 over the square root of 2 omega in e to the minus I omega k in. So this would be pure positive frequency modes. And as eta goes to minus infinity, A, the scale factor, goes to 0. So as A goes to 0, where do I have omega squared? As A goes to 0, just goes to k squared. So for the initial state, it's just going to be 1 over the square root of 2k e to the minus ik omega. Now, what is the motivation for choosing this? One motivation is as you go to very large k wave number, you're studying things on very small scales. And the very small scales that you're studying it should be insensitive to the space-time curvature, which is on a much larger scale. So if I'm in the universe and I'm very, very small, then I don't see the space-time curvature. It looks like, locally, it looks like Minkowski. And let's see, so let me continue this to the review. There's one more thing I'll write in terms of the review from yesterday. I'll call it 12, n plus 1. So at late time, eta going to plus infinity today, well after inflation, then there will be an associated number of particles in the vacuum, n out, so this is how you usually define the number operator. That is the number operator. So n out in the vacuum is a volume factor So remember, I can express A out in terms of the Bogolubov coefficients. So if I have, it's very simple to do this, AK out, dagger, AK out. I'm sorry, I have it the wrong way around. You could have earned a penny. Oh, it's a T.
A out, dagger, rotate, A out. I mean,
Here?
the order of dagger are different.
This order is different?
I meant dagger. A dagger A, not A dagger. Yeah.
No, that would define the vacuum. This is the number of particles. So when I do AK dagger of the vacuum, that's equal to 0. Okay? So AK dagger creates a particle, and then AK will destroy it. Okay? Sorry?
So you wrote the definition of the vacuum, so, and for the number operator, you do have A dagger A. So your vacuum has a 0 number.
It has a 0 number for the in here. So the vacuum state is set. This is the Heisenberg picture. It does not evolve with time.
Yeah, that's right.
So AK in defines the vacuum, but yeah, yes, okay, sorry. And in fact, what I have in my notes is this. Thank you.
Yes.
You know, I find in teaching that it's a little bit of far-sightedness. It's easier to see signs and factors of 2 from the back of the room than when you have the chalk in your hand writing it, even though it's right here in my notes. Okay, so again, this is just related to the Bogolubov coefficient squared. Then I will also write this in terms of the volume as a cubed n. I'm going to write it as a cubed over the volume. And this I will write this as dk over k, 1 over 2 pi squared times n sub k. So I'm defining an n. This is the co-moving number density. And this is the spectral density. So n sub k is 2 pi squared to the minus 1, k cubed times beta of k squared. All right, so here we see, as expected, a system prepared in the n vacuum will have some number of particles in the out vacuum at late time. All right, so in, 20 minutes, that's a review of what we did yesterday. And thank you for pointing out small typos. Let's see, do I have any board over here? Yeah, look at that. So something I didn't mention last time is now I'm going to define new mode functions, and I'm going to define chi k in, which is a function of eta. I'm going to define an alpha tilde, which is not the Bogolubov coefficient. This is e to the minus I integral over some eta prime minus beta tilde, which is not in general, the Bogolubov coefficient. E to the plus I integral, evaluated to eta. So this is going to be doing something like a JWKB approach. So I've defined new mode functions, alpha tilde and beta tilde. And at early times, we're going to take chi as so in other words, it's just going to be the pure positive energy solution. So eta, alpha tilde of eta going to minus infinity is 1, and beta tilde as eta goes to plus infinity is 0. Now, will this be a good solution for all time? Well, if you put this solution into the wave equation, so assume that this is chosen to be the solution at the initial value. If you would put this into the wave equation, just 1 over the square root of 2 omega times this, then what you would get from the wave equation is chi in double prime of k plus so if omega k does not change with eta, these two terms will not be present. This is prime, double second derivative. And this will be a solution to the wave equation for all time. But if these terms are large, large being sort of order 1 compared to omega k squared, then it will no longer be a good solution. So this will be the definition of expanding adiabatically. If it expands adiabatically, I can define an adiabaticity parameter, a sub k, which is a function of eta, as, let's not worry about factors of 3, sorry, omega k prime over omega k cubed. And if this is smaller than 1, then the solution will be adiabatic. So a sub k is going to be called the adiabaticity parameter. If it's large anywhere, that means the pure positive energy solution is no longer a solution, and you're mixing in negative energy solutions, and this is interpreted as particle creation. The alpha tilde and beta tilde satisfy I'm sorry?
Approximation.
Mm-hmm.
In order to write down the third equation, from the lecture yesterday, you have equation for the mode function, only frequency square, without the derivative terms of the frequencies. Now you have a derivative of frequencies, and you have square. I think I wanted to point out to get another penny, but the last two terms, do they come from the definition of your solution in this WKB approximation, or?
Yes.
I got confused about that.
If I put alpha tilde equal to 1 and ignore beta tilde, I can ask, is this a solution? It's a solution at initial time. So I'm choosing a solution at initial time. Is it a solution at later times? And the answer is no if these two terms are relevant.
I see, okay. I see.
Okay?
Okay, thank you. I missed that part, sorry.
I have confusion. So this adiabaticity condition is applying during the process, right? Not when you start like very far in the initial state, where in the past in the initial state. So, but I'm confused now, like because you're writing the in-state equation, and then you are, so that is eta going to minus infinity. So that should not have the adiabaticity condition, right?
It is adiabatic, so I'm going to write the A of k out in a moment. And you'll see that as eta goes to minus infinity, as A, the scale factor, goes to 0, A sub k will go to 0. So this is the nice thing about this cosmological model, starting with inflation, going to late times. At early times, it's adiabatic. And at late times, it's adiabatic. It's in the intervening time that it becomes non-adiabatic, and that's the signal we would interpret this as particle creation.
So you mean that inflation first period? We're talking about inflation like that?
Well, let me see. Let me write down explicitly what A sub k is. So for the scalar field model, A sub k is A squared m squared times h. So this is just taking the derivative of omega k squared. And this is r prime. Okay, it's just straightforward taking the derivative. Now you see that sorry?
I mean, in your note, you said, I think it's 3. The power of A.
The power of A here? You're right, it's A cubed. How did you see that? And again, what's that?
Yeah, it's a 3.
Thank you. All right, so as eta goes to minus infinity, A goes to 0. So the numerator just vanishes. H goes to a constant in de Sitter space. A goes to 0, this term goes away. A goes to 0, H goes to a constant, R goes to a constant, and R prime vanishes in de Sitter space. So in the initial state, AK is equal to 0. Deep in inflation, it's adiabatic. Now, as eta goes to plus infinity, we look at today, essentially it's Minkowski. And H vanishes, R vanishes, H vanishes, R prime vanishes, and again, AK is 0. So we start adiabatically with the expansion and inflation and end up adiabatically today. But in some intermediate time, intermediate values of h, a sub k need not vanish. Okay, so parameterizing the mode function in terms of alpha tilde and beta tilde, we can find the equation of motion for alpha tilde and beta tilde. That integral involving omega, and beta tilde prime is minus 1/2 a sub k So the equation of motion for the mode function chi sub k chi sub k is complex. It's a second order differential equation. The equations of motion for alpha tilde and beta tilde are two first order differential equations. So it's the same number of equations that one has to integrate. And again, you see, obviously, if the adiabaticity parameter is 0 or remains very small, then beta prime will be approximately equal to 0. And you're not going to populate the negative energy solution. Okay, two more things. Okay. I had an expression for beta of k. Now, pay attention to where the tildes occur, because beta tilde is not, in general, the Bogolubov coefficient. But beta of k, the Bogolubov coefficient, this comes from the normalization condition, the Wronskian condition. And we can evaluate the right-hand side as eta goes to infinity. As eta goes to infinity, the Bogolubov coefficient is static, but the right-hand side looks like it varies with time, but it doesn't. The time variation cancels. And these tildes here are the new mode functions, alpha tilde and beta tilde. The beta on the left-hand side is the Bogolubov coefficient. At late times, this goes to 0. So the Bogoliubov coefficient beta of k is the late time limit of beta of k tilde. And the final point I will make before I'll stop for a moment and catch my breath is that we know what chi k in is in terms of alpha tilde and beta tilde. And we can take the derivative of this, and we can express beta of tilde squared So we want to calculate beta tilde at late times, and we can do this in two ways. We can solve the mode equation for chi k directly. That's the second order equation used to be up on the board. Or we could integrate the equations for alpha tilde and beta tilde. And then we can find the late time value of beta of k tilde at late times. That's equal to the Bogoliubov coefficient, which is related to the number density of particles in the vacuum. So let me show you some pretty pictures. This is the solution for a particular value of m over h, set it equal to 1, and a particular value of the wave number k of 0.01. So the upper figure shows omega k squared as a function of a scale factor divided by AE. So this is the end of inflation at 1. So at early times, omega k squared is k squared because a goes to 0. So it goes to a constant. It would go to k squared. And k is 10 to the minus 2, so here it goes to 10 to the minus 4. But as the universe expands, the part of the of omega k squared that depends upon k squared starts to grow, and eventually omega k squared is, this is for conformal coupling, eventually it's a squared m squared. So eventually it increases as a squared. This is the adiabaticity parameter as a function of A. At early times, so the inflationary phase is here for A over AE less than 1, it goes to 0. It starts adiabatically. Then the adiabaticity parameter increases and becomes large around the end of inflation. And then the adiabaticity parameter decreases. Eventually today, it will go to 0 again. And it oscillates because H, the expansion rate, and A are oscillating because the inflaton field is oscillating about the potential. So you would expect as A becomes larger that n sub k related to beta of k squared becomes large. So here it's beta of k starts at 0, n sub k starts at 0. There's no particles of this wave number in the vacuum. Then as a sub k becomes large, the number of particles in the vacuum becomes large and eventually settles down. I love these figures. You're going to see a lot of them. Now, when you talk about the number of particles in the vacuum, you really can only define particles when the expansion is adiabatic. So in the initial state, deep in inflation, you can say how many particles are in the vacuum because the expansion is adiabatic. Today, the expansion is adiabatic, so we can define the number of particles in the vacuum. But in this intermediate state, I can't identify a number of particles when the expansion, when a sub k is large. My colleague at Chicago, Bob Wald, perhaps you've studied his book on general relativity, very formal mathematical physicist. He tells my colleagues who are the experimental particle physicists that it's impossible for them to define a particle today. It makes them very upset. You know, what is a particle physicist if you can't define a particle? Let's see what else. Okay. So here's another picture of n sub k. And again, it starts at 0 in inflation, and then it becomes large and oscillates around. This is for different values of m over h and k over a-e-h-e. The previous one was m is equal to he, and k is equal to 0.01. This is 0.1 and 0.1. I just love, so this is just solving the differential equation with boundary conditions. Second, it's a complex, chi sub k is complex. A sub k, alpha sub k tilde and beta sub k tilde are complex. You can solve the second order equation for chi k double prime or solve the two first order equations. You get the same answer, of course. So this is the result for conformally coupled a conformally coupled scalar. Now let's look at a minimally coupled scalar. Looks different. Yeah. Well, n sub k, again, we only can interpret number of particles when it's adiabatic. When it's non-adiabatic, you can't interpret it. So why do things behave differently for minimal coupling and conformal coupling? Okay, until I get an answer, I'm going to scratch my fingernails on the board. You don't want to hear that, do you? What's the difference between conformal and minimal coupling? Yes, omega, the scale factor can become negative. Not the scale factor. The angular frequency squared can become negative. So that is the difference. And writing n sub k in terms of the absolute value of beta squared only makes sense if omega k is real. So this is the indication that conformal coupling and minimal coupling is going to be different. the equation for beta of k prime involved a sub k times omega of k. And here I'm showing the value of omega k times a sub k for conformal coupling. I didn't write that anywhere. This is for a conformally coupled scalar. And this is for two values of k, a set of two values of k and m. The thing that enters into the differential equation, the parameters, are the wave number k and the mass m. Let's see, I didn't write what this is. M tilde will be defined as m over HE, the expansion rate at the end of inflation, and K tilde will be defined as K over AEHE. So the solid curves here are the numerical model for chaotic inflation, and the dotted curves are the analytic approximations gluing together de Sitter in a matter-dominated phase. So you see, if I glue together de Sitter with a matter-dominated phase, it's continuous here, but the first derivative is not continuous. And it's more important for m larger than k. So if m is larger than k, there's a noticeable discontinuity in the adiabaticity parameter. Now, the final remark I'll make before we break is when we talk about the number density of particles produced due to the expansion of the universe, what we're going to talk about is a cubed times n as eta goes to infinity. In other words, approximately Minkowski. So we don't want to talk about particles in this intermediate state. Now, infinity, let me make a statement. Infinity is a rather large number, right? So when I go to my computer, put in the differential equation and punch the button to solve it, I really want to integrate to infinite conformal time, but the computer doesn't want to do that. So what does it operationally mean to take eta to plus infinity? So operationally, To define the number density of particles, we want to have three things satisfied. One is the mode is inside the Hubble radius. In other words, K over A inside the Hubble radius, this is larger than H. You want the momentum of the particle to be larger than the Hubble radius. Or A smaller than K over H. During a matter-dominated phase, H is proportional to 1 over A to the 3/2. So A has to be larger than some value. We also want to define a particle and the number density, the mode to be non-relativistic. And non-relativistic means the momentum of the mode, K over A, is smaller than M. So this will be at the scale factor larger than K over M. And the third requirement is that A sub K is approximately equal to 0. Then it's street legal to talk about a particle. Okay, so let's break now. When we come back, I'll talk about the stress energy tensor. And when I calculate the energy density naively, you should be able to immediately tell me what the answer will be. Remember, this is quantum field theory. The answer to every question in quantum field theory is infinity. So we're going to have to renormalize and things like that, right? So this is a hint. If you're doing quantum field theory homework and you don't get infinity, you haven't done the problem correctly. Okay, let's take a break and I'll see you. M tilde will be defined as M over HE, the expansion rate at the end of inflation, and K tilde will be defined as K over AEHE. So the solid curves here are the numerical model for chaotic inflation, and the dotted curves are the analytic approximations gluing together de Sitter in a matter-dominated phase. So you see, if I glue together de Sitter with a matter-dominated phase, it's continuous here, but the first derivative is not continuous. And it's more important for M larger than K. So if M is larger than K, there's a noticeable discontinuity in the adiabaticity parameter. Now, the final remark I'll make before we break is when we talk about the number density of particles produced due to the expansion of the universe, what we're going to talk about is a cubed times n as eta goes to infinity. In other words, approximately Minkowski. So we don't want to talk about particles in this intermediate state. Now, infinity, let me make a statement. Infinity is a rather large number, right? So when I go to my computer, put in the differential equation and punch the button to solve it, I really want to integrate to infinite conformal time, but the computer doesn't want to do that. So what does it operationally mean to take eta to plus infinity? So operationally, to define the number density of particles, we want to have three things satisfied. One is the mode is inside the Hubble radius. In other words, K over A inside the Hubble radius, this is larger than h. You want the momentum of the particle to be larger than the Hubble radius. Or A smaller than K over h. During a matter-dominated phase, h is proportional to 1 over a to the 3/2. So a has to be larger than some value. We also want to define the particle and the number density, the mode to be non-relativistic. And non-relativistic means the momentum of the mode, K over A, is smaller than M. So this will be at the scale factor larger than K over M. And the third requirement is that A sub k is approximately equal to 0. Then it's street legal to talk about a particle. Okay, so let's break now. When we come back, I'll talk about the stress energy tensor. And when I calculate the energy density naively, you should be able to immediately tell me what the answer will be. Remember, this is quantum field theory. The answer to every question in quantum field theory is infinity. So we're going to have to renormalize and things like that, right? So this is a hint. If you're doing quantum field theory homework and you don't get infinity, you haven't done the problem correctly. Okay, let's take a break and I'll see you when? 15 minutes, 10 minutes? 15 minutes. Okay. 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 Let's see. Is this on? Okay, good. Well, let me say a word about the stress energy tensor, because what we're doing is solving the Einstein equation. And this is an operator, because we're doing quantum. And we're going to, we can use the Hilbert action to calculate T mu nu. And rho bar, sorry, rho bar, which would be, well, define it as the energy density measured by an observer with a 4 velocity u. So this would be the energy density measured by an observer with 4 velocity u. And in the observer's rest frame, of course, this is just as you would expect. Except it's 1 over the square root of 2g00. Because u, the general relativistic u mu u nu is equal to, u squared is equal to 1. All right, so, it's straightforward. We have the action. We can calculate T mu nu. And I'll just write what it is. Of course, it changes as a function of eta. This is going to be a quantum composite operator. And we're going to have to use the commutation relations. Omega k here. And then there are additional terms that involve one minus 6c. And one more term, you can calculate this, if you will, for homework. It's a rather boring calculation. Perhaps I've done it correctly. And as I hinted or said, it will be UV divergent. So we have to do some regularization. And you see in the literature two regularization schemes. One I will not employ. It's called adiabatic regularization, and it's a very complicated, in my opinion, unnecessarily complicated regularization scheme. But the one I will adopt is just involves normal ordering. Which is usually employed in just quantum field theory, Minkowskian quantum field theory. Anyway, when you do the normal ordering, there's some renormalized energy density. This is at late time when omega k squared is a squared m squared. So in the end, it's exactly what you expect it to be. The energy density is the number density times the mass at late times. And Na cubed is just related to beta of k squared. Okay, so here's the program in one easy slide. Okay, so we're starting at eta of minus infinity as the scale factor goes to 0, and starting in an inflationary phase, which is quasi-de Sitter. It's quasi-de Sitter because in true de Sitter space, H is a constant forever, but this is quasi-de Sitter. In inflation, the inflaton field slowly rolls under the influence of the potential. The quasi-de Sitter phase or inflation ends at some value of eta, which I'll call eta sub e. and the scale factor is A sub E. So the subscript E will correspond to the end of inflation and the beginning of a matter-dominated phase where the energy density is due to the scalar field oscillating about the minimum of its potential. This remains until the scalar field, until the inflaton field decays at some conformal time A sub RH for reheat, when the scale factor is A sub reheat. And then this will end up at eta equal plus infinity. A goes to infinity, in other words, today. So we're starting with AK in. The absolute value of that is 1 over the square root of 2K. This is a pure positive energy solution. This defines the vacuum. Then we can integrate chi k in from the mode equation and calculate it and find it at late time and evaluate beta k tilde in terms of chi k in squared and chi k in prime squared. And at late times, omega k is 1 over A times m, and there's a minus 1/2. We can integrate the mode equation for chi k, or we could, so omega k squared goes to k at early times, at the initial time, and at late time, it does whatever it does. It can be negative. At late times, it approaches A times m. So at late times, R goes to 0. A is much larger than K, so omega goes to AM. So I can integrate the mode equation with this value of omega K squared, or I could integrate the two first-order differential equations for alpha K tilde and beta K tilde. And I wrote these out before. This is the adiabaticity parameter, omega K, beta of K, and phi sub K is a cumulative phase of the field. And A sub K is omega K of eta over omega K squared. So this starts with A sub K equal to 0, starting adiabatic, and it ends adiabatic. N sub K is K cubed over 2 pi squared times beta of K squared. This starts at 0 with the assumption that for the vacuum, that we don't have any particles in the vacuum at the initial state. And we want to find the value of beta of K tilde at late time. And that will give us the mode density N sub K. Okay, so that's the program. So let's write a program. Results of I write it in Python. This is the number density, the mode density, N sub K. The number density is the integral dk over K times N of K, divided by AE cubed HE cubed. And this is what it looks like for a conformally coupled scalar, C equal to 1/6, with 3 choices of M over HE. And let's look at this curve, the blue curve, which is M over HE of 10 to the minus 1. For small values of K, small values of K tilde, it increases as K tilde squared. It reaches a maximum then it decreases as k tilde cubed e to the minus some constant, approximately 2 pi, k to the 3/2 over m to the 1/2. And I'll talk about how we can see this behavior. Then it's exponentially decreasing, and then there is another term at very large values of k. It no longer decreases exponentially, but it's going to decrease as k tilde to the minus 3/2. So but if you look carefully at this, it's not exactly k to the minus 3/2. There are some oscillations in it. And these oscillations are not very prominent in this case for a quadratic inflaton potential. But if one does a hilltop potential for a conformal scalar with a hilltop potential, the oscillations are quite pronounced. So generally it decreases as k to the minus 3/2, but the oscillations here are very pronounced. And on Friday, I will, if I have time, explain these oscillations as quantum interference in particle production. So just to tell you how, I had written this code to calculate n sub k, and I saw these oscillations, and I spent months saying, what's wrong with the code? It's giving these oscillations. I expected it to be k to the minus 3/2. Why are these oscillations there? It turns out that for large k, the differential equations you're solving become stiff. Computationally, it's a little bit difficult, but I just tried to figure out what was wrong, and it turns out, of course, nothing was wrong. It's due to quantum interference that I'll talk about. So I think the lesson might be sometimes you trust the output of your code. So I want to take some time now, probably for the majority of the rest of this morning, to say why we expect this to be k squared, why we expect this to have this form, and why we expect k to the minus 3/2 eventually. So let's look at solutions in the quasi-de Sitter phase of inflation. And let's just assume that instead of quasi-de Sitter, it's de Sitter. It's exactly de Sitter space. Then the early time solution in de Sitter space, we're looking for solutions to chi k double prime. And omega k squared in de Sitter space is k squared plus a squared is 1 over eta squared minus 1 over eta squared. Sorry, A is minus 1 over eta. A squared is 1 over eta squared. So this is, so with that value of omega, putting into the mode equation, the solution to the mode equations are always approximately going to be some type of Bessel function, right? So Bessel functions have to be your friend if you work on this. So the solution in the Sitter space to this equation involves Hankel functions, Hankel function of the first kind and the second kind, which is related to standard Bessel functions, index nu, so it's always going to be some combination of Bessel functions. So the solution to the wave equation in de Sitter space is in terms of the Hankel functions. The second order equation, so there are two solutions. Remember, in de Sitter space, eta is negative. Now, we want to choose C1 and C2, the boundary, such that it meets the boundary condition that chi k of eta to minus infinity is and with this boundary condition, C2 would be 0. So during the de Sitter phase, and nu here is the square root of 9/4 minus m squared over h squared minus 12c. So we're going to look at some special cases. Did I just erase what the solution was? And I guess I erase what nu is. Okay, now let's look at some special, right, good. Let's look at some special cases. Let's look at m, the mass equal to 0. And let's look at the conformal case of c is equal to 1/6. If c is equal to 1/6 and m is equal to 0, nu is equal to 1/2. So if nu is equal to 1/2, that's chi-k in. Now let's look at the case of minimal coupling. Nu is equal to 3/2. So if I look at in the low mass limit, and probably I should write this as m over h. So if I look at chi-k in squared as a function of eta, log of, let me do log of a over ae. It starts, as this goes to minus infinity, as 1 over the square root of 2k. And if c is equal to 1/6, it remains this value for the absolute value squared up until the end of inflation, which would be 1. If c is equal to 0, again, it starts as 1 over the square root of 2k, as eta goes to minus infinity. But at some point, it starts to increase. Once this becomes large in magnitude larger than 1, as 1 over eta squared, if I take the square of chi sub k, and that increases as a squared. So in the low mass case, I won't talk about the high mass case. In the low mass case, it's pretty simple to know what chi sub k is in the quasi-de Sitter phase, which we're approximating as de Sitter. Now, how does chi-k squared evolve in the matter-dominated phase? And let me suggest everybody take out your phone and take a photo of this. because I'm going to refer to it. Originally, I thought I could have this projected and then work on the board. But it's also in the notes that I sent. So I'm going to look at the evolution of chi-k by looking at approximation of the mode equation by starting at the end of inflation at a tilde equal to 1. This is the end of inflation. And the solutions will behave as a function of a depending upon whether it is relativistic or non-relativistic. So non-relativistic is low values of k smaller than a times m. Relativistic is k larger than a times m. And whether the expansion rate is larger than m or the expansion rate is less than m. So here I am approximating the matter-dominated evolution as not the numerical solution to the background inflaton equation, because that would depend upon the inflaton potential. I'm just assuming this is for a conformally coupled scalar in the matter-dominated era. So what I'm going to do is for a particular value of k tilde, k tilde is k over AEHE. I've defined that before. I'm going to start with the solution from de Sitter space, then look at the second order differential equation for chi sub k. It's a second order equation. There are two solutions. For the boundary condition, as I evolve in a tilde, I'm going to take the smoothly connect it to the solution in de Sitter space, and then it will evolve as a certain function of a, and then when it drops to the expansion rate smaller than m, I'm going to again consider the solution and match it to the boundary condition in that phase. So I'm following the evolution of chi-k squared in A, starting at de Sitter. I know what it is, conformally coupled, I know what it is here. It's 1 over the square root of 2k. And then follow the evolution and follow the evolution. And then when I get to another region, I'm going to match the boundary conditions of what it would be there. Okay? Now, in the matter-dominated era, well, it's always a squared, m squared. And a squared in the matter-dominated era and this is something, I think it was yesterday or maybe Monday, A over AE in the matter-dominated era is 1 plus, 1 so A squared for large values of eta tilde is eta tilde to the 4th over 16. So there are 3 basic regions when I solve the mode equation. The first region is relativistic. If it's relativistic, the K tilde term then is dominating. So this is K over A greater than M, or K tilde greater than A tilde M tilde. There's the non-relativistic region. And this divides into 2 parts, the non-relativistic region when the expansion rate is smaller than M, and the non-relativistic region non-relativistic, K over A is less than M, and non-relativistic when H is larger than M. And the other thing I will use is H is HE times A tilde to the 3 divided by A tilde to the 3/2, a matter-dominated expansion. So in the matter-dominated phase, for 1, in the relativistic region, the mode equation is simple. And of course, the solution, 2 solutions, chi k is some constant times a cosine and a sine. And matching to the boundary condition for de Sitter phase, pi k squared would be constant. So that was simple. It's not so simple when I go to the non-relativistic region. There, the mode equation is going to be second derivative of chi k plus eta tilde to the 4th, m tilde squared over 16. So solution is a wave equation, a solution, some sort of Bessel function, right? It's always going to be some sort of Bessel function. And according to Mr. Mathematica, the Bessel function is it's exciting to see all these factors. So this one term, this is a gamma function, and a Bessel function of index minus 1/6. Plus the other term, j of plus 1/6. And the argument of the Bessel function, the Bessel function will be different if the argument is small, much smaller than 1, or much larger than 1. So the Bessel function is equal to 1 roughly, approximately at A tilde is equal to M, when H is equal to M, and this will happen at A tilde equal to M tilde to the minus 2/3. All right, so in this region, it's non-relativistic. Up there, I'm sorry, in the top region, it's non-relativistic when k is larger than am, and chi-squared is proportional to a to the 0. In this region, it's non-relativistic. If h is larger than m, the argument of the Bessel functions are smaller than 1, and it's approximately equal to a constant in a. And if h is larger than m in the non-relativistic region, the argument of the Bessel function will be larger than 1, and chi k squared will be proportional to a to the minus 1. So let's leave that up there, and maybe I can just use this board. Can you see this board from that side? I'll be back in a moment. So let's see what chi k squared will be eventually in the late time as a tilde goes to 0. So it's going to be where it starts at chi k and it's going to be constant in this phase, and then when h is equal to m, when a is equal to m tilde to the minus 2/3, it's going to start to decrease as a to the minus 1. So this is 1 over 2k for the conformally coupled theory, m tilde to the minus 2/3 over a tilde. Now we can use what we are interested in is calculating n sub k. And this is 1/2 omega k chi k squared plus 1 over 2 omega k chi k prime squared minus 1/2. And we know what chi k is. We can calculate chi k prime. And at late times, omega k is a tilde times m tilde. So this ends up being 1 over 8 pi squared, m tilde to the 1/3, k tilde squared. So so multiplying by a tilde gets rid of that. If you multiply by m tilde times m to the minus 2/3 is m tilde to the 1/3. So this predicts that it scales as m tilde to the 1/3 times k tilde squared. And the reason I did this, I told you it would work. Right. This is proportional to k tilde squared. And as m increases, as m tilde increases, n sub k increases. So we understand for small k the behavior here of k squared, and we understand this scaling. Now for k larger than m to the 1/3, we're going to run into a problem, going the wrong way, because this model that we're using for m larger than k has that little discontinuity in the first derivative. Now recall the differential equation for beta of k tilde was 1/2 a sub k omega of k times alpha of k tilde and e to the minus I integral over eta evaluated at eta. Now, if beta of k is small, if beta of k is small, alpha of k is approximately equal to 1. So we can sort of set this equal to 1 if beta of k is small. So the evolution of beta of k looks like a type of Fourier transform. When this term becomes significant, it's going to filter out the low frequency behavior here. Okay, so there's a low frequency term, a slowly changing term here, and eventually at large eta, there's a rapidly changing phase. So the Fourier transform is going to be sensitive to abrupt changes in omega times A. And you see there are abrupt changes in omega times A if M is larger than K. So this approximation of trying to understand the behavior here of n sub k, we're not going to be able to employ this for m over k larger than 1. So we're going to need another technique to be able to calculate it. So we can understand the small k scaling of omega sub k, but for large k, we need another technique or two. So let me rewrite this in a little bit more detail. Beta of k prime, I'll put in the 1/2 integral and this is again setting alpha tilde of k equal to 1 if beta tilde of k is small. So how can we solve this? Well, it looks like once this is largish, you can do a steepest descent calculation. And this was done by Daniel Chung. This was his thesis at the University of Chicago. And sort of equivalent to a steepest descent calculation is the calculation done by Emma et al. Nope, J-Help. And finally, you can do a Stokes type calculation. These are all going to give the same result. And this was done by Hashiba and Yamada. and J cap. And it would take approximately, I suspect, 2 lectures to go through this calculation, but steepest descent calculations are something people have are familiar with. Stokes probably not so familiar with, but this is a very nice paper that explains it well. So all of these approaches give essentially the same answer, that beta of k squared is approximately e to the minus some constant, k tilde to the 3/2 over m tilde to the 1/2. And these work for k larger than m tilde to the 1/3. So the small k behaves like this. And this is valid for k smaller than m tilde to the 1/3. And then for larger k, the steepest descent calculation would give this result. But that's not the end of the story. So there's gravitational particle production beta. Where do I have it? Right. Beta of k changes here because of this slow, because of the slow evolution of this. And this is rapidly changing, but the rapidly changing part there also contributes to particle production. So you can think of the rapidly varying part as there is a condensate of inflaton particles that are oscillating, and you can have so after inflation, in the matter-dominated phase, you have a condensate of inflaton particles that are oscillating. So the energy density is in the homogeneous inflaton field oscillating about the minimum. So with this view, what is the number density of the inflaton particles? Because we're going to imagine we can have processes like the inflaton particles producing the KIAS. So what is the number density? Well, the energy density in the phi, these are the inflaton particles, is equal to m times the number density of phi. So these are cold inflaton particles. And the energy density in the phi, the inflaton is dominating the energy density of the universe, is m Planck squared times h squared. H squared is rho over m Planck squared. And in the matter-dominated phase, this is m Planck squared times He squared divided by A tilde to the cubed. Because the energy density, the expansion rate decreases as A to the minus 3/2, so H squared is proportional to A to the cube. Now, if we consider the two-body processes where there are two phi particles, as in the condensate in the vacuum, annihilating and producing two chi's, that process is going to be proportional to n phi squared. Okay? So what we're going to do is to consider processes where you have two inflaton particles producing a graviton, producing the chi's. And of course, this will only occur if m phi is larger than m chi. The inflaton particles are cold, they're at rest in order for this to be allowed. So here, the momentum of the chi is equal to the mass of the phi. All right, now we can take a Boltzmann approach and imagine n chi dot plus 3h n chi is equal to n phi squared times the cross section. And this is some thermal average cross section. Generally, there would be a term that's n phi squared minus n phi equilibrium squared. I'm sorry. So here I'm assuming that there is no inverse process where the chi's annihilate to produce phi's. And as usual, it's useful to calculate n chi a cubed dot. That will get rid of the expansion term. And this just turns out to be a tilde cubed over he cubed times n phi squared sigma v. Okay, so the next thing we have to answer is what is the cross section? And the cross section has been worked out by the Wu-Tang clan. If I say Wu-Tang Clan, does that mean anything to anybody? We don't, we have hip hop. Sorry? Yeah, but the Wu-Tang Clan is a very famous hip hop group in the US. RZA, GZA, Inspector Deck, U-God, Ghostface Killer, Method Man, Raycon, Master Killer, Capadonna, and Old Dirty Bastard. Nobody remembers Old Dirty Bastard? I guess hip hop is not very popular in Korea. So the cross section was calculated by the Wu-Tang Clan, and it depends on whether it's conformally coupled or minimally coupled. And for the minimal coupling case, sorry?
You mean that perfection depends on the Jai that connect to receive color to high skill?
Yes, yes. So generally, so to calculate this, you assume that G mu nu is eta mu nu plus something H mu nu over M Planck squared, and there's probably a 2 there, or maybe a 1/2, something like that, right? And so you start with the action for the scalar field, which depends upon R, and then substitute for G mu nu and pick out what H mu nu is. That's why R will enter and will make a difference. And the Wu-Tang Clan do a very good job of this calculation, and it's a very clear paper. All right, so did I write the cross section? Yes, I did. All right. So putting that in, so instead of integrating, because we know how time changes with A in the matter-dominated universe. Okay, so we have to think of this as a resonance reaction because the momentum of chi is equal to m phi. So the momentum of chi will be k over a and this is going to be m phi, and the phi is the inflaton field. So when k is equal to a times m phi is the value of a when the resonance occurs, when two phis will produce two chi particles. So I can, instead of writing d by dA, I can write it as d by dk. So you see here that n chi a cubed will be proportional to 1 over k to the 3/2. And surprisingly enough, this is here where this is proportional to k to the minus 3/2. So what I've done is to explain, so first of all, numerically calculate n sub k. I can show why this increases as k squared reaches some maximum, starts to decrease as e to the minus here, because we're filtering out, in terms of a Fourier transform, we're filtering out any slow component. And then eventually it goes as k to the minus 3/2. Now the numerical calculation is just integrating the mode equations. It's just using the Boltzmann approach. So you shouldn't think of this process, phi to chi, as something different than what would be obtained in the Boltzmann approach. So the Boltzmann approach is, in my opinion, the correct formalism, or the most general formalism to calculate particle creation. This formalism of considering two inflaton fields producing two chi fields is a good way of understanding this behavior. Furthermore, numerically, it becomes a very stiff system of equations out here. So it's numerically difficult to calculate, so that's very convenient. And if you want to understand the interplay between the Boltzmann approach and the Bogol-Luboff approach, where is Mr. Lee? Is Mr. Lee here? Lee? Stand up. Mr. Lee with his come on, stand up. Stand up. Take a bow. This, to discuss, the, not competition, but how to understand these two approaches, was in a paper, a very nice paper that he wrote. So that's it for conformal coupled theory. I will end up showing one more figure for conformally coupled theories tomorrow. Talk about minimally coupled scalars tomorrow, then go on to talk about gravitational production of fermions. I will talk about gravitational production of massive vector fields, gravitational production of massive spin 3/2 Rarita-Schwinger fields, massive production of gravitational production of massive spin 1 Proca fields, and gravitational production of massive spin 2 fields. But if we understand the formalism for scalars, it will be easier to understand the formalism for these more complicated theories. Okay, 12 o'clock, enjoy lunch. Thank you.